In this example, I'm trying to determine the convergence of an infinite series, the sum from n equals 2 to infinity of 2 to the n divided by 5 to the n plus 1. All right, now the trouble with most of these is what tests do we use? That's the big question. I see some different options. I think the ratio test might be applicable. That's a good Swiss Army knife of test. It works pretty much all the time or most of the time. But what seems most appropriate to me is the geometric series test, because just looking at the way this looks, it just looks like a times r to the n. I might need to tweak it with a little algebra, but I think that can be done. Now, another thing that concerns me, other than just the way that this term here looks, is I expect geometric series to start at 0, not at 2, and so we have a little bit of issue there as well. But to be honest with you, I actually picked this example on purpose because I want to show you how to handle this when your geometric series don't start off on the right track. Okay, so as far as fixing this term here that we're adding up, that's not too bad. You need something to the nth power. This is 2 to the nth. The denominator is 5 to the n plus 1. So I can pull out one of these factors of 5, and I think it'll look a lot more appropriate. So we'd have the sum n equals 2 to infinity of, you'd have 1/5, we'll pull that 5 out, and then we'd have 2 to the n divided by 5 to the n, right? And this is of course equal because 5 times 5 to the n is 5 to the n plus 1, so that's all fine. This guy can be simplified as 2/5 to the nth power just by properties of exponents and all this kind of stuff, and we have our geometric series. So let me jot it down one more time. Sum n equals 2 to infinity of 1/5 times 2/5 to the nth power. Now think, what were your criteria to have a geometric series converge? Well, it had to do primarily with the r value. The r had to be less than 1, strictly less than 1 actually, less than 1, but strictly greater than -1. If it was, then this series converged, and if it was outside of 1 or -1, then it would diverge. And so we look at ours. Here's our r value. Our r is equal to 2/5, which is in this interval, so that's a great thing. So this guy here will converge. And it actually converges absolutely, right? Which I'm not going to go into the details as far as what that means in this video. We covered that in a previous video, right? But yes, he does converge, which means that this series adds up to a finite number. Now, something else I wanted to do in this example was take it a step farther. If you remember a geometric series, there was actually something unique about that geometric series test that was not true for most of the other tests. If you had a geometric series that converged, you can actually figure out the number that it converges to. Normally, that's not possible with the ratio test and the root test and the integral test and those things. But if your geometric series converges, then the number that it adds up to is a over 1 minus r. A over 1 minus r. This is a formula that you guys should commit to memory if you don't already have it memorized. All right, now ours is kind of like that, but there is a big difference. Do you see the big difference between our series and a true geometric series? Hopefully you noticed that ours doesn't start at 0 like it's supposed to. Now what I can say is this. I can say that the sum n equals 0 to infinity of 1/5 times 2/5 to the nth power, which is not ours because ours doesn't start at 0, would be equal to 2/5, I'm sorry, not 2/5, 1/5 rather, 1/5 divided by 1 minus 2/5, right? Do that algebra. Let's see here. 1 minus 2/5 or 5/5 minus 2/5 would be 3/5. And then 1/5 divided by 3/5 would be 1/3. Okay. So now this is the sum from 0 to infinity. And what I want to show you or share with you is how you handle if it starts later down the road. Like in this case, ours starts at 2. So let's think about this for a minute. Okay, if I wrote this out long ways, what does it mean for this sum to be a third? That means if you take the n equals 0 term and add it to the n equals 1 term plus the term where n equals 2 plus da 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 da, and do that for forever, this sum from 0 to infinity would add up to a third, right? That's what this means. But ours goes from 2 to infinity. So think about this. We don't have the 0 term. We don't have the first term. Ours starts at 2 and goes to infinity. So how do you think we could figure out in some clever little way what our summation would be that doesn't go from 0 to infinity, but only goes from 2 to infinity? Well, the trick is this. Here's the trick. The trick is, why don't we, if you want the sum, and pardon my shorthand here, if we want the sum from 2 to infinity, why don't we take the sum from 0 to infinity, which is admittedly too much. That's too much. That's too big of a number. And then take this number and subtract out the first 2 terms, right? So check out what I'm saying here. If we took the whole sum, which was equal to a third, and we subtracted out the 0th term, and we subtracted out the first term, n equals 1 term, then what would be left, net result, would be the sum from 2 to infinity. It's actually quite smart. So here's what we're going to do. All right, so our summation, where is it? Right here. This will be equal to a third. Now, this guy by itself, this is too much. This is too much. It shouldn't be that much. Right? That's too much because that's the sum from 0 to infinity. Way too much, way too large. So we need to backtrack. We need to take away what this guy was when you plug in 0. 2/5 to the 0 is 1. 1 times a fifth is a fifth. I need to take that out. That wasn't supposed to be there. And when n is 1. So 2/5 to the first is 2/5. 2/5 times 1/5 makes 2 over 25. Okay, so this by itself was too much. I took out the 0 term, I took out the 1 term, and you can do that. You can take out a finite number of terms on the front end, and this net change will be the sum from 2 to infinity. All right, so we have a third minus a fifth minus 2 over 25. So let's calculator punch that a little bit. I'll tell you what, I'll clear this out because I don't really need it anymore. Need a common denominator. I think 75 would probably be about the smallest thing we could use. So we'd have 25 over 75. That's a third. And then we'd have minus 5 over, let's see, hang on. What was this? 1/5. I'm sorry. 15 over 75. That's a fifth. And then minus 6 over 75. 6 over 75, which is 2 over 25. I multiplied both by 3. I have a common denominator. 25 minus 15 is 10. 10 minus 6 is 4 over 75. And that's my final answer. So when we can use the geometric series test, we would prefer to use that test over, let's say, something like the ratio test, because the ratio test, sure, it could have told you that this series converged, but it could not have told you what it actually converged to, what these terms added up to. So this is a neat use of the geometric series test, and I hope especially that this trick about subtracting out the first few finite amount of terms made sense, because it's very likely that you'll have to repeat this for some of your examples.